Hello everyone. Let us look at one of the important theorems with respect to Poisson's and Laplace equation, which is uniqueness theorem in this video. Let us look at the statement of the uniqueness theorem first. It talks about the solution to Laplace and Poisson's equation, and it says if we find the solution to Laplace equation or Poisson's equation satisfying a given boundary condition, then the solution is unique, which means there can be one and only one solution possible for solution to Laplace equation, or this theorem is applicable to Poisson's equation as well. So when we look at the Poisson's and Laplace equation for a given boundary conditions, then the solution is said to be unique solution. So how we will prove the uniqueness theorem is, we can prove by contradiction method. As per the theorem, the solution is unique, which means only one solution is possible. But by contradiction, we are assuming if there are two solutions to the Laplace equation or Poisson's equation, we are going to prove that these two are not two different solutions. These two are the same solution. So that way we can prove this theorem by contradiction method. So when we look at the Poisson's equation or Laplace equation, this is a second order differential equation for potential function. For this second order differential equation, to solve it, we need a boundary condition. Now, when we look at the boundary condition, that boundary condition is with respect to electrostatic field problem. We will look at how to apply the boundary conditions and how to consider two different solutions for Poisson's and Laplace equations and prove the uniqueness theorem. By the contradiction assumption, if we consider V1 and V2 are two different solutions of either Poisson's equation or Laplace equation, let us consider two cases. One is for Poisson's equation, another is for Laplace equation. If V1 is the solution of Poisson's equation, then V1 must satisfy the equation, which means if we apply V1 and get this expression, this will be satisfying. So if we apply V1 here, we can write the equation as del square V1 equals to minus rho V by epsilon. And if V2 also is considered a solution to this equation, then del squared V2 must also be equal to minus rho V by epsilon. We are marking these two equations as 1 and 2. Now, similarly, if we consider another case or separate case for Laplace equation, if V1 and V2 are two different solutions, then V1 and V2 must satisfy Laplace equation as well. So we can write del squared V1 equals to 0 and del squared V2 equals to 0. So now let us mark these two as two separate equations. Now we are going to arrive at a common thing with this Poisson's equation and Laplace equation. If I subtract 1 and 2, 1 minus 2 gives me del square V1 minus del square V2 equals to 0. The same way, if I subtract 3 and 4 for Laplace equation, I'll get del square V1 minus del square V2 equal to 0. And this differential operator is distributive operator. I can write this del square as common, and I can write function V1 minus V2 for del square. So I can write del square of V1 minus V2 equal to 0. So this is a common equation, even if we consider the Poisson's equation case or Laplace equation case. And we can write this V1 difference V2 as a difference function. We know V1 in rectangular system, if I consider, it's a function of XYZ, and V2 is also a function of XYZ. The difference of these two will again be a function of XYZ. We can term it as V difference function, which is a function of XYZ. Now we can write this equation as del square Vd equal to 0. And we are marking this as equation number 5. Next, we should consider the boundary conditions. For any electrostatic field problem, at least one conductor surface will be there. So we will consider the conductor boundary as the boundary for any electrostatic field problem. And when we look at a conductor surface, the characteristics of conductor surface is it is equipotential surface, which means everywhere on the conductor surface, if we measure the potential, it is going to be same. Conductor surface is an equipotential surface. So if I consider, say, 2 points, 1 and 2, and if at point 1, if potential is V1, and if at point 2, the potential is V2, and we are considering this conductor surface is the boundary for electrostatic field problem. Any electrostatic field problem must have at least one conductor surface. So we are considering this boundary condition as V1 at the boundary and V2 at the boundary being equal because the conductor surface is equipotential surface. If this is equal, then we can consider the difference of these two is zero. That is, V difference function at the boundary of the conductor surface equals to zero. We are marking this as equation number 6. So we will make use of this equation number 5 and equation number 6 in our proof by contradiction method. And we will consider one standard vector identity related to any scalar function and vector function. If I find divergence of the vector A multiplied with scalar alpha can be written as alpha times divergence of vector A plus the vector A dot product with gradient of this scalar function, where we are considering this two are in rectangular system. Now, in our scenario, the scalar function is our V difference function, which is a function of xyz. And if I find gradient of this V difference, we can consider that as the vector function to be applied in this vector identity. So when we apply in place of alpha V difference function and in place of A vector gradient of this V difference function, we can rewrite this vector identity as like this. And we have to consider this on a definite region for evaluating the electrostatic field problem. We'll consider a volume which is enclosed by this closed surface S, and we will evaluate this parameter or this vector function over this volume enclosed by this closed surface. So in that case, we have to consider this expression of V difference function and gradient of V difference function. This has to be evaluated over the volume integration. So when we consider volume integration for the left-hand side and right-hand side, the left-hand side term and the right-hand side has two terms. Integration is distributive and we can write two integrations in summation in the right-hand side. So we'll get this expression as given. Now, when you look at this term, second term in the right-hand side, which is del Vd dot del Vd, these two are same vectors. Dot product of it will give magnitude of that vector square. So we can write del Vd dot del Vd as del Vd mod square. Now, in this, we can substitute the known equations just we have observed, which is equation number 5 and 6 to simplify further. So when you look at this expression, this del squared Vd can be taken as 0. This del squared Vd will become 0 when we take the case of equation number 5. In that case, this integration in the right-hand side become 0. So you'll be left with one integration in the left-hand side and one integration in the right-hand side. This is the del square of V difference function, which is always 0. And for the left-hand side, this is volume integration of divergence of the vector, where the vector is Vd multiplied with del Vd. This entire term is the vector for which divergence is taken and volume integration is done. By the known divergence theorem, we can rewrite this expression in the left-hand side in terms of closed surface integration, where divergence theorem says volume integration of divergence of D is equated to closed surface integration of that vector D. In our case, the vector is Vd multiplied with del Vd. This divergence of this vector function integrated over the volume can be written as closed surface integration of this vector function. So the left-hand side can be written in terms of closed surface integration, and in the right-hand side, only one integration is left, which we are writing as it is. Now, when we look at this, this is integration on the surface. When we look at the integration on the surface itself is a boundary. Boundary is the region separating one medium and the other medium. When we look at the surface, which we are considering as the boundary itself, we can apply the boundary condition here. So when we apply the boundary condition from equation number 6, which says V difference function is 0 at the boundary, thereby this term V difference is 0, which makes the integration in the left-hand side 0, which gives the integration of volume for del Vd mod square becomes 0. Now we have to look at how this integration will be 0, or under which condition this integration can be 0. So when we look at the integration of a function over the interval a to b, if this is 0, there are two possibilities when the integral can become 0. One is if the function itself is 0, or if the integration of the function, if it is odd, then it becomes 0, which means if the function f of x is equally negative and positive over the interval a to b, then this function is said to be odd function. Integration of odd function over this interval can be 0. But when we look at this integration function, this is a square function, del Vd mod square. Any square function cannot be odd. So the second case is ruled out. Only first case is applicable here, which means this function itself will be 0. If I consider this function itself as 0, then this equates del Vd mod square 0, or we can consider this as del Vd equal to 0, which means gradient of the difference potential equals 0. Gradient of any function can be 0 only if this function is constant. That means differentiation of any function is 0 only if this function is constant. In that case, we can consider Vd is constant on the boundary which we are considering. If Vd is constant on the boundary which we are considering, we can consider the boundary as equipotential surface, and on the equipotential surface, Vd is 0, which makes V difference V1 difference V2 equal to 0. That yields V1 and V2 are same. Thereby, we are getting V1 and V2 are not two different solutions. They are both the same solutions. Thus, we are proving the uniqueness theorem by contradiction method, assuming two different solutions and considering the known vector identity and our boundary condition at the conductor surface. We are proving the two different solutions assumed are not two different solutions. They are becoming same. Thank you for watching the video.